the graph data structures, and what we found is that graph can be defined, any graph can be defined as a set of vertices and a set of edges. So we write it as G equals V comma E. So there will be a set of vertices V and a set of edges E. And in the extreme case, can you hear me? Hello, am I audible?
Sir, in between your voice is breaking.
Can you hear me? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. The weather is really bad. I think, I don't know. There is a power cut also. So let me start and see if I can continue with the class. Okay, so we are talking about the graph data structures, and a graph can be denoted as a set of vertices V and a set of edges E. And we found that in the most extreme case. So have you started the recording? Did anybody start the recording?
Yes, sir.
I started, sir.
Okay. So this is a trivial case where a graph may have just one node and no edges. So that is the trivial example of a graph. And another case where it may have just some isolated nodes but no edges. or it can have a set of edges and the set of nodes, but they may not be interconnected. All of them may not be interconnected in a single component. So there can be multiple components, and a graph may be, in this case, it is undirected graph, where we consider these edges to be having no directions. That is, D is an so you can reach from D to E, and you can also reach from E to D while you are traversing the graph. So both ways it can be reached, but in this case, this is a, or in this case it is a directed graph. So from this particular node you can reach to this node, but may not be the reverse direction. So some graphs may be connected or disconnected, graphs may be directed or undirected, graphs may be having all the nodes of similar type, or it may be composed of uh, two partitions of nodes, two types of nodes like this, which we call often as bipartite graphs, like that. And generally a node may not have a connection to itself, or there is a the edge from a particular node may not go into the same node itself. Okay, so these are the variations of graphs. And what we found, say if this is the example of a small graph, or we also mentioned that large graphs, typically large graphs which composes of millions of nodes, are often known as network. Okay, it's a so large graphs are often called as networks. And in many real life examples we basically deal with large networks which composes of large number of vertices and large number of edges. But generally for uh, real world examples, the number of edges of a graph which is having n number of nodes, say if it is completely connected or fully connected graph or network, we would expect nc2 number of edges there. Okay, so that is typically large, so it will be a click kind of thing. So if you have got 10 to the power 5 nodes, and if each node is connected to all the rest of the other nodes, it will be a very dense graph. And generally such graphs do not occur, uh, uh, I mean, is not found in real life examples. So in real life examples, although we may have uh, typically very large number of nodes, but or vertices, but the number of edges are much less than that of the possible value, that is nc2. Or in other words, we can say that real world graphs are more or less sparse in the sense they have very few number of edges that is present. Okay, so when we talk about representation or storing the information of a graph or a network, then if this is the example given, what we found, we have to somehow store the adjacency information. So this is the adjacency information, means who is adjacent to whom. In this case, each node maintains that information. Total there are a b c d e f g h, these number of nodes, and each node maintains its adjacent node information in form of a list, say for example. So A says that my neighbors are C, D, C, F, D and all this. B says it is D and D, like this. And there are two alternative ways to store this adjacency information. One is in form of adjacency list, another is in form of adjacency matrix. So if we, so this is matrix of size n cross n. N is a number of nodes. In this case, total there are 7 nodes. So total there are 7 rows and 7 columns, and each cell within that matrix, which is denoted by I and J, it will be 1 if there is a connection or there is an edge between the ith node and the jth node. It will be 0 if there is no connection. Okay, so this is easy to encode. If we have an adjacency matrix, it becomes very trivial to encode this adjacency information. So if you consider a sparse graph or a graph where there are very few number of edges compared to the maximum possible number of edges, you will have lots of zeros in this particular matrix. And probably you are familiar with the term of sparse matrix. So this will be represented as, in that case, the adjacency matrix will be represented as a sparse matrix. And we know that there are various possible alternatives to store the sparse matrix, in form of a data structure. So I'm not going to those details. Those are already covered in your data structure course, I guess. So here, if this is the case, if we decide to store the graph information in form of adjacency matrix, we just declare a matrix of n cross n. And if you have already implemented a matrix class, it is very trivial to implement. So you just write a graph class and you try to say implement that graph class using. So there are two possibilities. You can implement the graph class as if it is composed of a matrix object. Okay, so graph class is composed of a matrix object, and then you can keep on adding its other data members or member data and member functions. So that is one way of doing things. You can also implement graph as as a matrix. Okay, so trying to privately inherit the graph class in a private mode of inheritance from that matrix class. So definitely graph as if it is composed of a matrix object probably is a better way to define the implementation. Okay, so once it is done as a matrix, so then you have to just access the ith element. If it is 0 or 1, you can keep traversing and you can perform various other operations. The other option is to consider the implementation of this adjacency information in form of a adjacency list. So there you have to we can store this information in form of a linked list. So it says that corresponding to each of these rows or each of these rows of this adjacency information or each node, you store a linked list. So this is one linked list. So corresponding to each node, you have got a linked list. Okay, and each of those linked lists will store the will have the number of nodes in that linked list will be equal to the degree of that particular node. Okay, so here the degree of A is 3 because it has got 3 neighbors. So the degree means the number of neighbors. Okay, so degree of a node. So we can think of that corresponding to each node there will be a linked list, and the number of nodes or the node count of each linked list will be equal to the degree of that particular node. So A has got degree 3, it will have 3 nodes. B will have its degree is 2, it will have 2 nodes, like that. And in fact G is isolated node, its degree is 0, that's why there is no nodes connected to it. So that is pretty trivial. Now let us see that how we can implement it using our uh, previous class definitions. So if you look into this part, is this visible, the screen? Can you see the screen?
Yes, sir.
Okay, so as you can see here that there is a node class like this. So I am just trying to show the my linked list class. So it will be a collection of linked lists. So this is a node class, and followed by that we have got the singly linear linked list class, which says that it has got a head node, and the head node will in turn will be connected to the nodes as we insert node into that linked list. So like that, and these are the different member functions which can operate, which can manipulate the linked list. So here, as like the hash function, we can implement the graph also. So the size, if we try to draw the analogy, the size of the hash table, in this case it will be I mean the number of nodes. In case of graphs, it will be the number of nodes. Okay, and then as definitely there will be no hash function, but instead of writing say SLL asterisk HT, you can write here GT, like that. So maybe something like this, SLL GR, that is a graph, and then you have got total number of nodes that you stored here. Okay, and then you have got a graph constructor, the graph destructor, and then you have got the display function, the create adjacency list, like this. Okay, and within the okay, we can implement we can implement the graph data structure something like this. We have got a list of nodes. So if there are n number of nodes, we will have 0 to n minus 1 number of linked lists, and each connected to this one. Now let us so I think you can, I mean, if you go through that hash table class, you will be able to implement the graph class also, right? And in this case, whenever, so maybe the input to the graph class maybe something like this will be, say if I've got a graph like this, say 1 2 3 4, then say 5 5 7. Okay, so if this is the graph, so the input to the graph may be provided in form of a file, or maybe provided as an input when the code is running. So we can think of that it will be something like this: 1 2, then 1 3, then 2 4, then 3 5, then 5 7. Okay, so this way you may input the adjacency information of a graph. Okay, so from here you can, or maybe before you do that, you can write a value that is 7 here, or maybe, okay, so it should be 6. So the value 6 here. So the thing is, the first input will be the number of nodes, and whatever it follows in each row, it's a pair of node IDs which is considered to be an edge, which is representing an edge. Okay, so if we input this, so if you start with a graph which is a pointer to a linked list like this, so initially it will be all null, and so when you construct the graph, you basically construct in this form. Okay, and you may recall that there are uh, two fields in each node. Can you recall that? Each of these node structure, it has got two fields. One is the info field, one is the extra field, and one is a link field. Okay, so each node will have this kind of, this is a node structure. So it's the info field, extra field, and the link field. So now in this case, we can use the info field to store the degree of the graph. Okay, so here we can store the degree. This extra field sometimes may be useful. Say if we go for graph traversal, so when you are traversing a graph, if you have already visited a particular node, during your traversal you may set it to 1. So initially, before you start the traversal, you can set the extra field or this particular information, this particular field of that head node to be 0, and once it is traversed you can set it to 1. That means signifying that that particular node has been traversed. So each of these linked list signifies the stores the information of 0th node, 1th node, 2, 3, 4 like this. So in the info field we basically store the degree of this node 0, degree of node 1, degree of node 2, and here in the extra field, if requires, we can store some additional information. In this case it may be the visited information in case of traversal. Okay, so that can be the policy. And once you have constructed this trivial graph data structure, so you can call adjacency, create adjacency list method. So within that method, either you open a file which stores information. The weather is really so. How long things will go wrong? Well, so the geo is still working anyway. So either you can expect this as a file, maybe a text file which stores this adjacency information. So in that case, in the create adjacency list, you have to open this file and read one by one the information of line, each line. So this 6 means you have already created this one. So now this is 0. So maybe I have started counting from 1 instead of 0. So it's 1 2. So whenever you write in a read in a particular line 1 2, or you input 1 2, that means in the 1th node, on the 1th linked list, you have to add a node saying that 2 is a neighbor of the node 2 is a neighbor of node 1. So this is say node 2. Okay. So will that be enough if I write 1 2 like this? When I read 1 2 in the input, if I add 2 as a neighbor of 1 in the linked list 1, will that be enough? Hello? Am I audible?
Yes, sir.
So if I read, say, I am reading it from a file, or maybe you are inputting it. So if I read 1 2, so that means it says that I would like to have 2 as a neighbor of 1. So that means in the adjacency list of 1, I want to add a node with the value 2. Will that be enough?
Yes, sir.
So we need to add 1 in 2 also.
Now, will that be enough? So if I do not duplicate, so if 1 comma 2 is enough, the entry is just 1 comma 2. If it is an undirected graph, so if it is a directed graph, it is fine. So that means 1 is connected to, you can jump from 1 to 2. There's a directional arrow. But if it is a undirected graph, so if it is a directed graph like this, it is fine. But if it is an undirected graph like this, that means what? As 1 is a neighbor of 2, 2 is also a neighbor of 1, right? Or as 2 is a neighbor of 1, the reverse is also true. 1 is also a neighbor of 2. So what do I need to do now?
Add the direction.
Got the point? Got it? So you have to add 2, a node with information 2 in the linked list 1, and you have to also add a node with information 1 in the linked list 2. Is that fine?
Yes, sir.
So now if I read 1 3, that means I would like to have 3 as a neighbor of 1. So I'll add this node. Okay. But at the same time, once I keep doing this, I will be incrementing this value, because this, say, probably I mean that here in the info field, I would like to store the degree. So initially it was set to 0. as I add a neighbor in that particular linked list, a neighbor of that particular node. So the index of each link of this each row is basically the node ID. This information is corresponding to node 1. This is node 2, like this. So once I add a particular node here, I should increment this info field of the head. So this is basically the head of each linked list, right? So once 3 is added, it will be updated to 2, and now I should treat 1 also as a neighbor of 3, and therefore I have to add like this, and I have to increment it by 1. Is that fine?
Yes,
Is
sir.
that okay? So in that way, I keep scanning through this text file that has been provided to me as the information of the graph. Now once I have scanned it and I have prepared this entire adjacency list, I am ready to process the graph, right? So this, if we look into the linked list class already, which is already implemented, as I mentioned, as a data member, you should write SLL asterisk gr, and in the constructor you should uh, allocate space. So this is gr is a pointer to a node or a head node, right, which corresponds to a linked list, singly linear linked list. So in the constructor, as you will see, or as you have found in the hash table, you will be allocating an array of such nodes and pointing, and the base address of that array will be stored in the gr pointer. Okay, so once we have done that, we call create adjacency list, where we would scan through this file, or we'll take input and we'll populate this adjacency list. So once these two steps are done, the graph data structure has been created and it has been updated with the information of the graph that we would like to process. Okay, and as I mentioned, so the second field, so in each node, maybe, so this is treated as a header node and these are the internal nodes, but all the nodes, these boxes are having the same number of members or same type of members, same structure, right? So here this information is stored for some special purpose as it is required, and this also, here also we can use something useful if we need to. Okay, so once this is done, let us come to the DFS, okay, depth first search. And I think all of you are aware of the logic and all this, but let me just once again uh, try to check the logic. So if this is a graph given, so what we generally do in DFS, what we generally do in DFS, DFS, how to implement DFS. If I, so this is basically the this uses recursion. Okay, so this DFS is using recursion. You see, this DFS is calling this DFS again. If I don't use recursion, I can use stack data structure to implement it, right? DFS using stack. So what is the purpose? This purpose is to go for a graph traversal. So if this graph is given to us, so what is the approach? How to implement it using a stack traversal? What is the first step? So the first step is to call the method or procedure with say, maybe I start with say A. Okay, so I start with A. So what is the first step? I push A into the stack. Okay, so I don't mark A. Basically, I don't mark A, but I push A from some node I start, so I mark it as I push it in the stack, and then I call the DFS procedure. Okay, so once I call the DFS procedure, the first step is it should pop out this. Once it pops out, it first will check that whether it has been visited or not, because it is basically graph traversal, means you are trying to visit the nodes of the graph in a certain sequence. So right now A has not been visited, so you mark it as visited and you display it. So here is the uh, display sequence in the DFS. So we just display the value of that node information, that is A. What next we do? We try to explore the neighbors of A. So how many neighbors A has got? How many neighbors A has got? Hello? Can you hear me?
Yes, sir.
Yes, sir.
So how many neighbors A has got?
3, 4, 4, 4. Sorry, 4.
How many? 3 or 4?
4.
4.
4.
Okay. So the logic says that, I think you also are aware of the logic. So the thing is, you have to scan through all the possible neighbors of it. So these are the 4. And what to do, if a particular neighbor of A is not visited means it has not been marked or tagged, then you try to uh, push it into the stack. Okay, so A, where from I get this information that A's neighbor is E, I, F and G? Possibly from the entry of the linked list of A. So I can scan through it. So how many, what is the degree, and what is the state, so like whether they are visited or not. Okay, and where from I get it? So if I say I am just so A is said the node 1, then I say that it has got 2 neighbors, 2 and 3, and then I check 2. So I can, using this index of 2, I can see that whether what is the state of this value, whether it is visited or not. For 3 also I can check this value and figure out whether they are visited or not. If they are not visited, in this case none of the neighbors are visited, so I just push them one by one into the stack. So maybe I push here E, then F, then I, then G. Okay, now once I have done that, now I go back and check that whether the stack is empty or not. If the stack is not empty, I again pop one element from it. G is popped, and if it is not visited, in this case it is not visited, I mark it and I display the content, the value or the information of that particular node. And I explore the neighbors of G. So how many neighbors are there in A? Hello?
Yes, sir.
So how many neighbors are there in A? I know these questions are tricky, but try to interact. Otherwise, it's difficult to know that whether I'm still connected or not. So how many neighbors of G are there?
2.
2 neighbors. And what is the logic? So you have to push into the stack all the neighbors which are not marked. So in this case, which neighbor will be pushed? B will be pushed into the stack. Okay. Now once B is pushed, then you again go back and check whether the stack is empty. Stack is not yet empty, so it pops out one element. So B is popped out, and now B, what is the logic? Is there any neighbor of B which is unexplored or unvisited? B has got one neighbor G, but G has already been visited, tagged. Where from you check it? So you get into the linked list corresponding to the node B, and you check one by one its neighbors. And from the neighbors you so if you know it's G neighbor, you straightway check the tag field of G, okay, and figure out whether it is visited or not. If it is not, if it is already visible, you do nothing. So I mean, once you pop out B, definitely you have to mark it and display it, and then you have to explore its neighbors. So this part is done. Now it again goes back and checks whether the stack is empty. It finds that it is not empty, so it will pop out I. So I gets popped out. So the first task is mark I and display I and explore the neighbors of I. So what do you think? How many neighbors are I has got, and what will be the action taken? Hello?
Yes, sir.
How many neighbors I has got?
I 4. Sorry, 3. 3.
3 neighbors. And how many
Yes.
will be pushed into the stack?
2. Because he is already
E
there.
and F, but they
Yes, sir.
are already there. So what do you think? What can be done? Will they be once again pushed?
Shouldn't be.
Hello?
Shouldn't be pushed, sir. Only E and F will be pushed.
Yeah, but to know that whether that they are not, so they are not inside, you have to scan through the stack. That is not possible. Stack does not support you to go deep into it and find out which elements are there. So straightway, although there is uh, redundancy in the elements that are pushed, but still you can push here E and F, right? So you can push here, and then you can go back and say that not getting to pop out E. So E is displayed, and you see that what happens now? F is an unvisited neighbor of F E. So you push it there, and you again check the status of the stack, which is non-empty. Pop out this one, mark it, display it, and then you find that F has no other neighbors unexplored or unvisited. So now no pushing of the stack is done, and so okay, so F has been already popped out. So now still the stack is non-empty, so it will pop out once again F and will find that it has already been marked and visited. So it will do nothing. Again go back and it will pop out E because the stack is not yet empty, and finds that E also has been marked. So it will do nothing, and it will find that now the stack is empty, so the traversal is done. This is the DFS order of traversal for this particular graph. This particular graph. Okay. So if I write the logic for this, so DFS so this is DFS of X. The first thing that I do is push X. So before I do this, think of the implementation, we have to declare a stack, right? A stack object we have to declare. So where should I declare the stack? I'm trying to implement the method DFS, graph DFS, and the method in the graph class. And there I find that the DFS requires a stack object uh, for implementation. So where should I declare the stack object? And I can simply include the header file, stack header file, and I can just create the stack object. But where should I create the stack object? Are you getting my question? Hello? Hello?
Yes, sir.
So where should I declare the stack objects which is required? I'm talking in terms of the graph class. So do I declare it globally outside the class definition? Do I declare the stack object as a part of a data member of that graph class, or do I need to or is it enough to declare it as a local object within that member itself? Got my question?
Yes, sir.
What do you think it should be added? It should be declared. Are you getting my question, or I mean, things are? Can you follow the class?
Yes, sir.
No, so try to answer the question. This is a more or less trivial question. Somebody should try to answer it. Are you all listening to the class, or you are just logged on? That's all.
Okay.
Hello?
Sir, we are listening.
So is the question clear what I'm asking?
Yes, sir. Yes.
We have got a graph class. So class graph. So within this we have got, say, SLN GR, and then we have got the constructor, the destructor. Okay, so the details like this, and then we have got create adjacency list. That also we can find out how to do this. I mean, it's already done, say for example, and then we are trying to write the graph DFS. So my question is, and we find that this graph DFS, it requires a stack data. So where should I declare the stack data structure? Will it be here? Will it be here? Or will it be here? Let us assume that we have included my stack.h. Where should I declare the stack data structure? I mean, a stack object. Position 1 is 2 or 3. Still it is not clear, or what's the problem? Hello?
Yes, sir.
Where it should be declared? Are you not getting things? I am asking repeatedly. Anyway, so if this happens, I can stop the class.
Sir, can we do it?
So tell me the problem. I mean, are you not following, or are you not getting things, or you are losing track of the class because the last class was long back? It took place in a long back. So what exactly is the problem? Just tell me. Otherwise, there is no point of talking. Keep talking one way, and then uh, what's the point? Can you follow the class?
Yes, sir.
Yes, sir. Yes.
So please tell me the answer. I have to write here stack S, and within that stack only I can push those node IDs, say for example. So where should I write this? Here, here, or here?
Sir, third number.
Hmm?
Number 3, sir.
The number 3 inside
Number
DFS.
3. I mean, it seems that number 3 is fine because there is no point of putting it. So definitely, if you put it here in position 1, so that means you are trying to. So anybody can access it. So there is no point of having it here globally. If I put it here, that means it is meant for something uh, which more than one method can access. But right now, as it appears to be that the graph DFS method is only using that stack object, right? So we can we can just declare it inside this stack, inside this particular method. So here in doing so, as you can see, we are using the SLL class methods or SLL class definition. We are using the stack definition. So that way we are using this to implement the graph data structure. So now let us come to the logic part. So I mean the pseudo code. I think the rest you can implement in your program. So first of all, I push whatever element I have started to traverse with. So in this case, it is A or B or whatever. So after I push, what is the next step? Next step is I check while it is not is empty. So if it is not empty, the stack. So who is not empty? So I can write here stack, say S. So if S dot is empty, it is not. Okay. Then what I do? What is the logic? We just now explained. What is the next step?
Pop is
Hello.
pop. So
We have to pop. So we pop something. Say let us assume that we have popped something. Say Z. Okay, or say T. The node ID that we have popped is T. So after we have popped, what we do now? We check that if the node T is visited, is already visited. We check if the node T is already visited. If it is not already visited, how to check it? We simply check this header node of that of the linked list corresponding to the node T. So if it is 3, so I just check this value. If it is 5, I just check this value, the extra value of that, because the extra field we are storing them. So I just check that part. If it is not the case, then what I do? I display T. That means just writing C out, and what I do? I mark T as visited. Okay. That means if it has not been visited, so that extra field of that particular linked list corresponding to that node T will be now set to 1. Once this part is done, what next? We have to explore the neighbors of T. So what this exploration means? You have to check the linked list corresponding to T, and you have to check as many number of nodes are there from the node count. You can write a for loop and you can check each one of them whether they are marked or not. Okay. So if they are not marked, you push it. That's all. So the logic is for all neighbors of node T. Say we are talking about some node, say Y. We just see that if Y is not yet visited or tagged, as you say, then we just push Y. Okay. That's all. So whatever this is done, it is not in the else part. So this will be done and this will be done. So if you have pushed something, so this is done. So then after that it will go back and check that whether the stack is empty or not. If it is not, it will pop out one element. If it is not visited, it will display and mark it as visited. It will explore its neighbors and push all the neighbors which are found to be not visited, and will again go back. So this whole logic will be repeated, and they will be visited in this fashion. Is that part clear?
Yes, sir.
So this you can write in the pseudocode. So the construction of the linked list, I mean the construction of the graph class, that was trivial because you can take help of the hash class, the construction of the hash class, and the destruction of the hash class. Now this create adjacency list, I have just now mentioned how to do that. You have to, for I and j, entry of I space j, you have to make a node of j in that linked list I, and the node entry I in the linked list j. That is done for all the edges that has been inputted in the file. And then if we call the graph dfs, so this way the graph can be traversed. Now, so let us assume that we are calling here dfs say 0. So from the main, if you call simply dfs 0, it will dfs graph dfs 0, some node value, it will go there and it will traverse it. Now if the graph is having say multiple components like this, so this is one component, this is another component, so this is the entire graph. It has got two disjoint components, two isolated components. So will this work if this is the logic?
No, sir.
Will this logic, the whatever the pseudocode is written, will it work? Hello?
Yes, sir. It should work.
How can it work? So this part, see these nodes marked black, they have. So if you start with a, if you have started with a, you have started with input to this node, I mean in this graph dfs, if you input the node id of a, so this part has been traversed. But what about this part, the blue part? How to modify it a little bit? Got my question?
Yes, sir.
How to modify it a little bit? So
Sir,
whenever you're calling this one, you just write here, say uh, for I equals to 0, I less than total nodes I plus plus. So if you have got any node unmarked, okay, so you are basically scanning through what? You are scanning through this list of header nodes, which each corresponds to a uh, graph node. So you are basically scanning through this part, this particular extra field. So in the extra field, if you find that if the ith node is unmarked, if the ith node is unmarked, you call graph dfs with I. Okay. So once you come up with a node which is unmarked, this will ensure that all the nodes which are connected, which belongs to the same connected component as like I, will be visited. So if you started with a, all these nodes belonging to the same connected component to which a belongs will be visited. But that may not be enough. So once it is done, you return back to this particular method, what do you need to do now? What do you need to do? You have to put it in a while loop and make sure that all the nodes are marked. Okay, so here, or you can write here, do while maybe a flag you set, the flag equals to, if the flag equals to true, you go back and check, and once you don't find this, so each time before you start checking, you set the flag to false, and once you have found something, so you can set a flag, and if you find the flag is, so none of the nodes are found unmarked, so then the flag will be set to false. Okay, so set it to true, and then it will then exit. Okay, so it will make sure that even if one node has not yet been visited, it will pass on that node information, and you will try to traverse the component corresponding to that node which remains unvisited. Is the logic okay? Is that fine?
Yes, sir.
So that way, if you have got three components, three disjoint components of the graphs, this graph DFS will be called 3 times. Now, if you would like to find out the size of each component or the number of nodes in each component, how to find it out?
Sir,
Hello?
can you repeat that?
Yes.
Can you repeat what you just said? Your voice was cracked.
My question is, so now there are two components. Say for example, I can display two components, C1 and C2, and maybe each time it enters, you can write simply like cout new component. You can write a new component, and all the nodes that are displayed, it says that it belongs to a different component like that. So maybe these nodes followed by C, H, and D. My question is, if I would like to know how many nodes are there in the first component and how many nodes are there in the second component, what modifications do I need to make? So I would like to also have not only the display of these nodes in this component C1, I would like to have the information of 1, 2, 3, 4, 5, 6. So it must say that total 6 nodes in the first component, total 3 nodes in the second component. So what minimal changes can I make to make it to extract that information?
Sir, in the for where we are checking if the node is if in the for loop we can add a we can define a counter that every time it goes to graph DFS the counter increases by 1.
Which one? Are you talking about this one? This
Yes,
for
sir. Yes, sir. That one.
this for loop.
Yes.
So how that serves the purpose? My point is, I would like to, if you add some counter here, I mean, so this counter each time it enters here, it will remain unchanged. So you will increment the counter and do it. So you can find out how many components are there. That is fine. But I am talking about how many nodes are there in each component.
Sir, we can return from the graph DFS function.
So how to keep track of it?
Sir, where we are displaying T, we can increment the counter and return the counter.
Where we are
Displaying the display
displaying
T.
T. Okay, so that is fine. But you see, one simple thing can be like, instead of just passing the value of I can pass the value of another value C. Okay, so this I call it as C. So this C is so what is this C? So C, every time I uh, say plus plus or C plus plus, so every time I call this graph DFS, the value of C is incremented. So C basically, before it enters here, C is set to 0, and C may be a part of uh, the the graph class itself. So C is a counter which helps us to count or to label these nodes. So if I write C equals to 0, so in the first case when it enters, calls graph DFS, it calls with value 0. And here whenever you are marking this, mark T as visited, mark with the value of C, mark with C. Mark with C means, that means all these nodes which are having this, so this will be marked as 0 0 0 like this. Okay, so this, instead of just putting a tick, I just mark them with all zeros, okay, in their empty field. But when I, once it is done, it returns back, I again see that there are some still unvisited nodes. I increment C plus plus, so it C is already incremented by 1, so C equals to 1 it takes next time, and it will mark these nodes as 1 1 1. Okay, so these will be 1 1 1, all these are 1. That means some of the nodes in this, some of the nodes empty field will be marked as 0, some of them will be marked as 1, some of them will be marked as 2, and all this. So they are basically, we can basically label those nodes, and once this whole process is done, we can just read that in extra field and figure out how many ones are, how many zeros are there, how many ones are there, how many twos are there, like that. And that will give us the size of each component. So we can, the final summary can be like, there are 5 components, and the distribution of the sizes, or the sizes of each component is this like this. Is that fine?
Yes, sir.
Is that okay?
Yeah.
So we can make use of that empty field in a suitable way as we find it here. So definitely we can modify it as this comma some C, and that way it will go on. So when we check it is already visited or not, we just check whether it is less than 0 or not. So maybe we start it with 1, so that we initialize the empty field with 0, and we start it with 1, so that it will be marked with 1 1 1 1, and then 2 2 2 like this. And already visited, we have to check that whether it is 0 or not. If it is non-zero, that means it is already visited. So using this, if you are given with a large graph or a large network, and if you are asked to find out how many disjoint components are there, it is possible. And if you are asked to find out the sizes of each components, that also is possible. And you can probably uh, display the distribution of the component sizes. Okay, now in a graph which has got a single very large component with typical features which can be well defined, we say this is that is a giant component. So generally for real world networks which is meaningful, we have got a single large giant component and several small components in the periphery. So maybe that this is a single large giant component composing of maybe say 90% of the nodes, and there are a few small components like this, and maybe some isolated nodes also. So that's a I mean the kind of view of most of the real world uh, graphs generally. Okay, so now if you think of like in such a graph, we are trying to study some dynamics. Say I'm trying to shoot or remove some of these nodes at random. Some of the nodes at random I'm trying to shoot. So what is going to happen? So once a node is actually removed or deleted, it will, so these edges in this edge information also will be deleted. So the edge corresponding to, so if this node is deleted, so this edge and to which it is connected to, so this edge information will be deleted. So a node removal means you will have physically in this data structure two such boxes will be removed, right? And one node removal means you get hold of this particular And
Sir,
hello,
you were not audible for the past 2 minutes.
can you hear me now?
Yes, sir.
Okay, maybe that there's a network problem. So what I'm telling is this one. So is this part clear, or we're not able to follow this? This one, this diagram.
Sir, can you repeat?
Yes. So the thing is, what we found, given a graph, given a large graph, using this logic, we can traverse through all the nodes and figure out how many components are there, right? And we also can figure out what is the size of each component. So we can have a fair amount of idea that how the nodes are interconnected and how many disjoint disjoint components are there and all this. Okay, how many groups are there? Say for example, in a friendship network, we can say that how many small friendship groups are there who do not interact with each other, right? So that can be a thing. Now maybe that generally what we find, even in a class of say 180 students, if you think of if you allow people to make friendship and they start working together, or solving problems and all this, talking to each other, you will find that uh, I mean, as such, in terms of the normal dynamics, you will find that generally there is a single very large group or component that is formed where people know each other and talk to each other, right? But there are few small groups which are also formed, those who probably are not well connected to the rest of that very large group. Okay, so this very large group, which comprise of 80% or 90% of the nodes, is often called as giant component. So this is a technical term. So it's a giant component. And this, when we say we are talking about a network, we basically talk about the features of its giant component. And we probably ignore in most of the cases these small components, which may comprise of a very small fraction of nodes, or maybe the isolated nodes also. Okay. And sometimes when you talk about the dynamics in such network, so maybe that if I ask you to remove this particular node, so this particular node removal means along with that node, all the edges corresponding to that node also will be removed. Okay, so there will be some changes in that adjacency matrix as an effect of the node removal. And once we remove or randomly remove say 5% nodes, one can again run this code to see that what kind of uh, say deformation in the structure that has taken place. In other words, how many components it has been disintegrated to. You again remove another 5%, means from 5% to 10% if you remove, then what is the amount of damage that has been done in the structure. So the idea is, I mean, one can study, or generally people are interested to study something like this. So percentage node removal, and this is the number of components with their sizes, and we'll find that so with the size means I mean the fraction of the node. So the size of the giant component, so generally it is found that if you remove say 5% node, still the giant component is remains. 10% still the giant component remains. So the thing is, if you remove 5%, 10%, 20%, it is sometimes not possible to disintegrate that very large component, the giant component of that network. But there is a critical value. Okay, so critical percentage of node removal, which if you withdraw, I mean if you remove from that, the whole giant component gets disintegrated into very very small networks. So you say that the entire network structure collapsed. So that has got a very nice dynamics. And in fact, theoretically, if the degree distribution of the network is given, these values can be calculated also. Okay, so in the complex network theory, one can calculate that what fraction of nodes if you remove, given this network with these features and the degree distribution, the whole network or its giant component will collapse and the network actually disintegrates completely. Got the point?
Yes, sir.
Hello? So definitely this is not the the area that we would like to study, but there are various say uses of this information of this component size and the number of components and the impact of the node removal on the component and all this. Okay, so in the assignment I would expect you to implement this logic using DFS, and which uses the stack data structure, the stack object, which has already been implemented, and this graph data structure also, which you can implement a little bit by looking into that hash data structure. So try to focus on two main functions or methods. One is the DFS, graph DFS, and create adjacency list. And node removal, okay, let us not I'll not give that assignment right now. So this part, so try to store a graph in form of adjacency list, try to traverse it using DFS, and try to come up with the component information, number of components and their sizes. So that will be the assignment. Any queries on this?
No, sir.
No, sir.
Okay. And as you can guess that if I implement it using an adjacency matrix, things will be pretty simpler, to access. So these logic will be the same, but uh, accessing will be pretty simple. Removal means, or if you have to check whether I is adjacent to J, you don't have to traverse the linked list, rather you have to just check a particular cell in the matrix, and it will work. Okay, so this will be the assignment for this week. I'll upload the assignment by tonight. Have you completed the previous assignments on the exception handling, templates and all?
Yes, sir.
Yes, sir.
Hello? So all are done, right?
Yes, sir.
Okay. So once the graphs are done, maybe in the next class I'll try to talk about the tree data structure. So one example of tree, and then we'll switch on to the STL. Maybe one class on STL, that's all.
Okay, sir.
Okay, sir.
Hello?
Yes,
Hello?
sir.
Yes.
Now you're audible, sir.
Whenever a call is coming, it gets disconnected to the hotspot. That's the problem. Anyway, so do you have any questions?
No, sir.
Okay.
No, sir.
Okay, I'll upload the assignments by tonight. Thank you.